A chord is a segment whose endpoints are on the circle. So it's any line that goes through a circle and hits the circle two places. That is a chord. So we can see there's a chord here. A to B is a chord. And if I would draw a line here, sometimes it stands out a little better here. If I draw a line from A to B, that is also a chord. That's a chord. Just 2 points in a circle, it becomes a chord. The next thing we talked about is a diameter. A diameter is a very specific chord. A diameter is a chord that cuts your circle in half. It cuts it into two hemispheres, or not hemispheres, but semicircles. It cuts it into two semicircles that have a 180-degree arc. That's going to be important today, knowing that the arc cut by a diameter is 180 degrees. That's going to be important today. Maybe I should write that a little more clearly. Because the circle is 360, so you cut it in half, and you have 180. All other chords divide the circle into what's called a minor arc, that is less than 180, and a major arc, which is greater than 180. So if we look at the arc, or the chord I just drew, this would be our minor arc. And we would name it by doing arc AB. Remember, we'd write AB and put a little mark over it. That's the shortest distance to two letters. The major arc would be this big long one that goes around the outside. I would label that one as arc maybe ACB. You need 3 letters to say you're going the long ways around. All right? So chord AB makes 2 arcs. Arc AB and arc ACB. All right, then we talked about 2 angles. Let's put that on pause really quick. I do first want to go over, did anyone have any questions on that homework that we did in class right before the break? So that would be that 9.1a. Okay, then we'll go on to expanding on that information. So one of the things we learned last week was something called a central angle. Your central angle is an angle that touches the center of your circle. So it's an angle that comes from the center of your circle. In other words, it's 2 radii making this angle. Well, if you ever have a central angle, the measure of that angle is also the measure of the arc that it subtends. So the measure of an arc is equal to the measure of the central angle. So if we look here, we have angle EGF. That's a central angle. Since that's 65 degrees, that means the arc it subtends, so from F to E, is going to be 65 degrees as well. That doesn't mean it's 65 centimeters, all right? I don't know the actual length of it. It's just the arc is 65 degrees. It's 65 degrees out of 360 of our whole circle. So once again, our central angle is the same length as the arc it subtends. What we're going to see down below is kind of what we're going to be doing for homework. We're going to be getting pictures, and we're going to have to piece together the information that we have in order to solve for a missing angle. This first one probably won't show too much of in the homework because it's a pretty easy one. We are looking for that little mystery mark here. I'm going to go ahead and I'm going to put an X over it. I hate question marks. I like when it's just a variable. So I'm going to do variable X. You can leave it as a question mark. I don't care, whatever you want. So we're going to solve for X. If it looks like a central angle, it is in fact a central angle. There is no tricks here. A central angle is going to have a big old point right there, and you're going to know it's the center of the circle. So that's automatically a central angle. You don't have to ask me. All right, if there's a big point on it, it's a central angle. So that's a central angle. Well, a central angle is going to be the same measure as the arc it subtends. So that X is actually going to be 120 degrees as well. Our next one, we're supposed to find the measure of FD. Well, we look at to D, and I can get part of it. I can get part of it because do we see the central angle right here? So this arc from E to D must be 81 degrees. So let's go ahead and mark that 81 degrees. So that comes from that central angle there. The other bit of information that you can get is this 135 is going to mean this distance from B to F is also 135 degrees. You might not always have to write it, but you should at least picture it every single time you see a central angle, know that the arc is the same. That means I just need to find the distance from F to, not the distance, but the arc FE. I need to figure out what degree that is so I can get the F to D. Do you have any thoughts on doing that, Sam?
135 is on a straight line.
It's on a straight line. So what's the measure of that arc?
F to E or B to E?
B to E. 180. Yeah. That's going to be something you're going to need to recognize a lot of, is the fact that anytime you have a straight line, that is a diameter, so it cuts the arc into 180 degrees. So that means that we have just 180 minus 135. What other color do I have? I guess a nice brown. So that little section from F to E is going to be 45 degrees. So our entire measure from F to D is 45 plus 81, which is going to be 126. Trust me, those 180s are going to sneak up on you. You're going to be, there's no way I can get this. Look for a straight line. Yeah, Hamza.
Do you also do vertical angles?
You can also do vertical angles. Yep. So if I would have known that one, I could have went across here. The problem with vertical angles is it's not going to help me too much. Where it could help me is this is 135, so that means that this is also 135, so I could get that measure. Once again, it still didn't quite help me, but you should be looking at that stuff. You should be looking for vertical angles. You should be looking for 180. You should be looking for central angles. The next thing we're going to talk about are inscribed angles. All right, but vertical angles still apply. All right, the next thing we're going to talk about is an inscribed angle. A central angle goes to the center, central center. An inscribed angle goes to the back of the triangle. So all 3 points are actually on the, not the triangle, they're actually on the circle. So if you look at A, B, and X, all 3 of those points are on the circle, where X is way back here. So we're made up of 2 chords. I have chord AX and I have chord BX. So chords make up inscribed angles. Radii make up your central angle. All right, it says the measure of an arc is twice the measure of an inscribed angle. So if we look there, we have AXB is an inscribed angle of 34 degrees. The arc at subtends needs to be twice that size. So this arc is going to be 68 degrees because you're just going to do 2 times 34. And it kind of makes sense if you think about it as like just a pure visual. I get pulled way back here. If you look at kind of what a central angle might look like, that central angle needs to be bigger than that inscribed. The further out you go, the smaller your angle has to be to go up and down. So our inscribed angle is always going to be half the measure of the arc, and the arc is always going to be twice the size of an inscribed angle. So if we're looking down here, it says find the missing angle or arc. What's the measure of angle BAC? Cam?
40.
It's going to be 40 degrees. Yeah, that's exactly it. It's going to be 40 degrees. Because to go from the arc to an inscribed angle, you have to do 1/2 that 80 degrees. So this is going to be 40 degrees. Sometimes inscribed angles are going to be kind of hidden. So if you look at that next drawing, that 35 degrees is not just an error of placement. That 35 degrees is this measure right here. But if you look carefully, that is an inscribed angle. It is the inscribed angle FEP. Inscribed angles can be hidden. It is 2 chords. All 3 points are on the circle, so it is in fact an inscribed angle. So since that's an inscribed angle, we could then say that the measure from E to F is 70 degrees. It is twice that 30 degrees. And I'm supposed to find that measure of that missing section, D to P. How am I going to find that? Cece.
Since everything has to equal. Okay, well, there's a straight line, so it has to equal 180.
There you go. There's a straight line, that has to equal 180 degrees. So that has to be 180 degrees. So that means that hidden distance has to be 180 minus 70, so that must make this distance 110 degrees. Which we could put... did we want to put that yet? I'm going to make sure that we didn't do it somewhere else. Yeah, we'll just put it as that 110 degrees. Questions on inscribed or central angles? Those are the easy stuff today. Those are just measures of angles, either the same or you multiply by 2. So remember that, a central and inscribed angle. They're either the same, which is central, or twice as much, which is going to be an inscribed angle. What you see here is going to be huge for this section. This could be taught in like several different lessons, but it's only 3 main theorems that are going to be the core of this homework and moving forward. All these are going to deal with chords. And our first one isn't too bad. It says 2 minor arcs are congruent if and only if their corresponding chords are congruent. Note the if and only if just means it goes both directions. So this says arc AB is congruent to arc CD if and only if AB is congruent to CD. So if BA is congruent to CD, that means the arcs they cut are also going to be congruent. You could go the opposite direction. If arc BA was congruent to CD, that would mean BA is congruent to CD. Just keep track of that. That 2 chords that are the same length are going to cut the exact same arc. All right? Chords of the same length subtend the exact same arc. Now we're going to get slightly more, not really complicated, it's just stuff you have to keep in your head every single time you're looking at these pictures. So this next one says the perpendicular bisector of a chord is a diameter or a radius of a circle. The perpendicular bisector of a chord is in fact a diameter or a radius. What you're looking for in a picture, you're looking for a 90-degree symbol and these 2 congruent symbols. As soon as you see both of those things, you automatically know SQ goes to the center of the circle, whether that be a full diameter or if we cut it off and it's just a radius. So a 90-degree symbol and 2 congruent symbols here will automatically mean that that line that's the perpendicular bisector is going to go through the center of the circle. Once again, it doesn't seem that hard, but it gets hard when we have a bunch of drawings and you have all this. This is to get us to a bonus fact. And we'll see what this means in the next one. So the bonus fact says, if a segment from the center of a circle, so any segment that goes through the center of the circle, is perpendicular to a chord, then the segment bisects the chord. So once again, if the segment from a center of a circle is perpendicular to a chord, then the segment bisects the chord, and we'll talk about that in just a second. I want to go down to this last one. It says 2 chords are congruent if and only if they're equidistant from the center. So two chords are going to be congruent if they're the same distance from the center. So if we look at that drawing, it says, hey, AB is congruent to CD if and only if EF and GE are the same lengths. That's what that distance check is. So chord CD is congruent to AB as long as this distance is the same as that distance. I also want to bring in that bonus fact really quick. That bonus fact says, if a segment from the center of a circle is perpendicular to a chord, then the segment bisects the chord. I'm going to do that drawing on here. Notice GE is perpendicular to CD. Based upon that extra fact, we would then know that CG is congruent to GD. These really just take practice, guys. You really have to take your time on the homework. The more you work on these, the easier they become. You're just going to see 90-degree symbols and know what it means in a circle. You look at congruent segments and know exactly what it means in a circle. Right now, these are just kind of arbitrary facts. But the more you start using them, the easier they become. So let's go ahead and think about these as we solve these two examples. So our first example says, in the picture below, DE is congruent to JK. So this chord is congruent to that chord. Keeping that in mind, some things that might show up is they cut the same arc. And that's about all we have for that just right now. So we have those two chords are the same length. It says J to K is 30 units long. This is the way I label it. A lot of times the full length from J to K is going to be 30. That way I'm not putting too much marks on there. Well, JK is the same length as DE, so that must mean that DE is also 30. Okay, it also says that JX is 17. J to X is this kind of dashed line right there, is 17. We're supposed to find X, Y. What could we use from the theorems up above? There's actually a lot going on there, and a lot of theorems that we could use. What are something that could help us, or at least we can do something with? Aryan.
You'd say, like, if a segment from the center of a circle is perpendicular to a chord, then the segment bisects the chord. So, like, that would be JK and then XC.
Mm-hmm.
XC is bisecting JK then. So
Yeah.
it's a perpendicular bisect.
Absolutely. So Aryan was just saying, well, if we go back here, it says the perpendicular bisector of a chord is a diameter or a radius of a circle. Bonus fact, if a segment from the center of the circle is perpendicular, are these segments from the circle perpendicular? Yeah, they make 90 degrees. That's what perpendicular is. So that fits that first part. If segments from the center of a circle is perpendicular to a chord, then the segment bisects the chord. So because this is in the center and is 90 degrees, it cuts JK in half. So that means JZ must be 15. Oh, let's do green. And it means that ZK is also 15. It bisects them. We could also do that to DY and YE because it's the same exact fact. Enza.
You just do like the Pythagorean theorem to find XZ.
Sure. So you see that triangle there, right? So let's find XZ. So let's pull out that triangle. Let's pull out that triangle. So I got this triangle. I got JXZ. I have a hypotenuse is 17. JZ is 15. It's actually a Pythagorean triple. Does anyone remember this Pythagorean triple to go right to the answer? 15, 17. Take a guess. You could be wrong. 8. It is 8. Yeah. So by using Pythagorean triples, you could say that this is 8. What if you didn't memorize the Pythagorean triple? Yep.
A squared plus B squared.
A squared plus B squared equals C squared. So you could do the x squared plus 15 squared equals 17 squared and solve it for x equals 8. Or you know the Pythagorean triple and you save that whole time. All right, so right now we have xz equals 8. What's xy then? Yeah.
8.
How is it 8?
XC and X bar are congruent.
How do we know? I'm not disagreeing with you one bit.
I don't remember.
Two chords are congruent if and only if they're equidistant from the center. So that means if two chords are congruent, their distance also has to be congruent. So we just used the kind of reverse of this one. We said, okay, my chords are the same length, so that must mean they are the same distance from the center. So our chords are the same length, JK and DE are the same, so that means YX and XZ must be the same length as well. So like I said, if you take your time and you work on these homework problems, you might not remember the exact theorem, but you're going to know it by the drawing. So XZ equals 8. So that means that XY also equals 8. Yeah, hands up.
Can you explain one more time why we know XY is also 8?
And it comes from this one here. This says if two chords are congruent, they have to be the same distance from the center. So DE and JK are the same length, right? That's what they told us. So the distance to the center has to be the same length. And it just happens to be XZ and YX. So that's what the theorem says, that if you have two chords that are the same length, this line that's perpendicular that goes to the center must be the same as this line that's perpendicular to this one. Okay? All right, the last one is a huge chunk of what you're going to need to do for your homework. It's not going to have the picture drawn. You're going to have to draw it, and you're going to have to solve it from there. All right, so we have in circle C. So we have circle C. So I'll draw circle C. We have chord AB is 12 centimeters away from C. If the radius of circle C is 18, what is the length of chord AB? Note, it doesn't tell you where to draw chord AB. So you can draw it anywhere you want. I'm going to go ahead and I'm just going to draw it up here. I'm going to call that AB. The only thing we know about AB is it does not go through the center because it says it's exactly 12 centimeters from the center. So since it's 12 centimeters from the center, what you're going to do is you're going to draw a line that goes from the center, put a 90-degree symbol on it, and you're going to put a 12 right there. That is what the distance from the center will look like. It's going to be a straight line that goes from the center and makes a 90-degree. I need to know the whole length of chord AB. What should I do? Sam? What about the radius of 18? We could draw it. Where should I draw it? Where do you want me to draw it?
I don't know.
Not sure? Shana? What if we draw it C to B? Right? So you have a really good point. Or we could have did it from C to A. So if I draw my radius down here, it's not really helping me in the drawing. So if I'd write, this is 18, it's not really helping me. But if we draw it exactly where Ishana told me to draw it, which is right here, now I have a right triangle. I now have a right triangle that I can bring out and say, okay, this is 90 degrees, this is 18, this is 12, let's call this x. I could solve that. I could do my x squared plus 12 squared equals 18 squared. Oh, is it 324, 324. All right, so x squared is going to equal 144, which equals 320, not 3 plus, I forgot a plus in there. There should be x squared plus 144 equals 324. We subtract 144 from both sides, you should come up with x squared equals 180. Then we'll take the square root of both sides and come up with x equals square root of 180. 180 is really big. It's probably not simplified. So now we have to think about a perfect square that goes into 180. What perfect square goes into 180? Yeah. 9 does. There's one bigger, though. There's a bigger one. Yeah. 90 does not a perfect square, because it'd be 30 times 30, which would equal too big. Yeah.
36.
It is 36. So we can rewrite this as square root of 36 times square root of 5, which will be 6 square root of 5. So I'll make this 6 square root of 5. How do I get that other side? Yeah. They have to be congruent. There's 2 ways to check to make sure they're congruent. The first one we can look for is basically if you have a right angle, it bisects it, which it does. And the other way you can check it is just, well, if I draw the 18 on there, it's the same triangle. So even if you're solving this and you forget the theorems, just kind of fall in. So that's 6 square root of 5, which means the other side is also 6 square root of 5. If I have 6 M&Ms plus 6 M&Ms, I have 12 M&Ms. If you have 6 square root of 5s plus 6 square root of 5, you are going to have 12 square root of 5. So you can add square roots as long as they have the same base. You could not add those if those was 6 square root of 2 plus 6 square root of 3. It'd be like saying you have 6 M&Ms plus 6 Skittles equals 12 Skims. You couldn't say it, right? So if you can't say it with M&Ms and Skittles, you can't do it with square roots. All right, but that's a lot of how you solve these. A lot of these are drawing triangles and solving those triangles. Don't forget about your radius. Anytime, just like Sam said, I forgot the radius, right? You just got to ask yourself, where's the best place to draw that radius that can help me in this problem? If you're just drawing it off to the side, that's fine to hold on for later. But think about where that locks into your problem. All right, guys, the rest of the time will be for you to work.